All right, this video is going to cover entropy balances and Carnot efficiency and the entropy equations needed to do compressors and turbines, but compressors and turbines is next video. Okay, so what is the entropy balance equation? It looks kind of similar to the energy balance equation, but it is slightly different. So delta S, so before we had delta E equals stuff. Here it's delta S equals M S2 minus S1, and these are state lookups, so you can look them up as a function of temperature and pressure and whatever. And that equals the sum of Q over TB into the system minus the sum of Q over TB out of the system plus the sum of MS into the system minus the sum of MS out of the system plus Sgen. And Sgen always has to be positive or zero because entropy of the universe always increases or is zero, but it's technically never zero in the real world. Okay, so like the energy balance equation where the left side was kind of internal energy and the right side was like external-ish energy, left side internal energy, right side external energy. So this is pretty straightforward, so I'm going to focus on the right side. These two I'll go over in a second when I do the Carnot efficiency. These two are like the MJ. So if mass is entering or leaving the system, use the state of that mass to find the S, and then include that in this equation. That is literally it. Okay. So what about this stuff? So let's do the Carnot efficiency. I did it down here, but I'm going to do it up here as well. I did it down there for practice. So the whole idea is you've got a heat engine. You've got a heat engine. So you put in some heat from a hot surface. I know this is kind of abstract, but if you Google Carnot equation, this is how you derive it. So it's QH because it's coming from the hot surface, and it goes to either producing work or the rest of it will go down to the cold surface. And you're like, what even is this? And I said the same thing, but it is kind of useful sometimes. Water break. Okay. So, big question. Why can't all of the energy that you put in, so QH, go into the work? What's the maximum amount of QH that can go into producing usable work? And that is what the Carnot efficiency tells us. Because it's not 100% and it is dependent on the hot and cold temperatures that the energy comes from. So what's the math for that? So a normal efficiency of this engine would be the amount of useful work it produces over the total amount of energy you put in, which is Q hot. Cool. And you can rewrite this as, so work is the difference of QH minus QC. So you can rewrite it, those cancel out. Well, you got QH over QH minus QC over QH, which is just 1 minus QC over QH. Cool. Let's let that sit for a second. Okay, now let's bring in our entropy equation. In this case, there's no internal mass, and there's no mass flowing in or out of the system, because there's just no mass. There's just heat moving around. So what are we left with? We are left with 0 equals, all right, fine, I'll just write it this way, but I'll copy it so I don't have to write it. Plus Sgen. Cool, so that's what we're left with. Now, ideally, in a perfect world, Sgen is 0. We don't produce entropy, because if we're producing entropy, that means we're doing something less efficiently than optimal. So in our optimal case, we don't produce entropy. Cool. And also we only have one Q in and one Q out, because we just have QH and QC. And work doesn't count as a Q out because work is technically perfect. So it doesn't produce entropy. That's why it's not in. Oh, I literally freaking moved it. I thought I copied it. That's fine. It's literally not even in the entropy equation. Okay. So ideally, that goes to 0, and we're left with 0 equals QH, in our system, by the way, is the heat engine. I should have written that earlier, but that's fine. Cool. And we can rewrite this. QC over TC, QH over TH. Cool. Okay. Well, that is pretty much it, because we can rewrite this again as, to match what's up here, C over QH equals TC over TH. So then we can rewrite what we have up here as 1 minus TC over TH. That's a Carnot efficiency equation. And what that's telling you is, let's say your temperature, your hot temperature is 400 Kelvin, and your cold temperature is 200 Kelvin. This is telling you that your max efficiency, maximum possible efficiency, is 200 over 400. What is that, 0.5? So it would just end up being 0.5. So 50% efficient. So it's saying no matter how good your engine is, no matter how efficient the engine is, the highest efficiency that it can possibly get is 50% efficient, which is kind of interesting. Because you would think the highest efficiency of any engine is theoretically 100%, but it's not. Cool, so that's kind of it. All right, with Q over TB, it is TB is boundary, by the way. Yeah, I should have said that earlier, but that's fine. Q over TB can be pretty friggin' rough. So, for example, I think I used this problem in the last video. If you have, like, let's say air going through a pipe, and let's say it's hot air, T1 equals like 500 Kelvin, and T surrounding equals maybe it's not that bad. Well, theoretically it's not that bad, but when you get into the weeds it is bad, so I'll explain that. T surrounding equals like 100 Kelvin, and the final temperature somewhere between those, let's say it's like 300 Kelvin. So as the fluid's going through, it transfers heat through the pipe wall out to the surrounding environment because the surrounding environment is colder. So you could get a total Q between state 1 and state 2. Q equals H. The Q that left, well, I don't care about plus or minus, so I'm just going to say H1 minus H2. That'll get the amount of heat that leaves the system. And it's going over this surface, which is technically, well, that's the weird thing. Because the surface, chances are, the surface temperature of the pipe is, I don't know, let's say it's 400 Kelvin up here, and let's say it's like 200 Kelvin down here. That's kind of the weird thing, is because the temperature changes, so you kind of have to integrate it, or maybe you could just, you could assume Q, I think this might actually be the way to do it. You could assume Q goes out to infinity, and at some point, the temperature, no, this, it would look like that. It would be kind of sloped. At some point, this could all be abstract, and you could just skip this part, but at some point, you enter roughly T surrounding. You'd enter it more closely on this side from heat transfer because you're at 300 Kelvin versus on this side you're hotter at 500 Kelvin, so it'll take a longer distance to get up to roughly T surrounding. But then you could say Q over TB equals the Q that we calculated down here. So I'll just write it. H1 minus H2 over TB, which is just T surrounding. Yeah, that might be the way to do it for this problem. And what else would you have in this problem? You wouldn't have this because there's no internal energy. You would have this, so you would have to look up S in and S out. Like, let's say we know P1 and P2, and I told you the initial and final temperatures. You could find S by just making it a state function. Yeah, okay, so I'll leave that there. The last thing, so there are two other entropy equations that are pretty freaking useful. Flipping pages here. They're going to be used in the next video. So the first one, delta S equals CV ln T2 over T1 plus R ln V2 over V1. Now there's a way to derive this. I didn't dig that far into the weeds, so I'm not going to derive it here, but my teacher probably derived it in my class like a couple of years ago. Dang, it's been a couple of years, what the heck. So that's the first equation. This also equals Cp ln T2 over T1 minus R ln P2 over P1. Cool. So what this is saying is if you have a box and you compress its volume down to a smaller size, assuming you do it perfectly, so assuming this is 0, you can use this equation to find the final temperature. Let's say you know V1, V2, and you know T1. You could use this equation to find the isentropic final temperature. Likewise, let's say, this is literally the next video. Let's say you have a compressor. And you know T1, P1, and you know P2. You can use this to find the isentropic T2S. You can use this equation and set this equal to 0. And for Cp, I think you would use maybe the average of the two temperatures. Same with Cv. I think that's how you'd do it. But yeah, that's it for entropy. This stuff can get a lot more complicated, but I'm kind of just leaving it at what I remember and what has been useful to me since. But I'm sure there was one homework problem that used this frickin' equation to the moon, and it took forever. But yeah, that's it. So again, big picture. Let me move this back up. Copy, paste. Big picture. Write that down. Write this down. And write this down. Cool beans.